Okay, let's get it going. 2 Zooms and full screen. Maybe one more Zoom. All right, how's everybody doing? Good. Okay. Again, we expanded the class. Everybody who's on the wait list should have gotten moved off of the wait list into the regular class already. If that is not the case, then it's probably the case that the system doesn't realize that you're on the wait list. So make sure that you bring that to somebody's attention and your program or Megan or me or whatever it may be. I think you have until Thursday to get all the forms or permissions or whatever needs to happen for you to be in the class. So that would be a good time to make sure quickly that that gets taken care of. Does anybody have any questions about that, your situation? Okay, so we've had a few decent posts and comments and whatnot on Campus Wire. However, the number of posts and comments we've had on Campus Wire is smaller than the number of people who haven't even signed up or on to Campus Wire yet. Easiest way to fail class participation is to not even sign up for the thing that you and the rest of the class are ostensibly participating in. There's no way you can comment on somebody else's question or answer if you don't even see them. Or if you are commenting on them, no one can hear you. So get signed up for that and get engaged in the conversation that, a few other people have started to get going. So that, decent first start. We just need everybody to be involved with that. Okay, so on the participation note, except not really, the YouTube videos have not been picking up your questions, so it's kind of hard to hear what it is that I'm answering. So we have got all the way from Finland, brand new Stan microphone. So if you have a question, we also have a new TA. We're selling, right? Okay, so we'll demonstrate how this works. Someone will throw it to the TA. TA will throw it to you. You will ask a question, throw it to the next person that has a question, or the TA, or me, whatever. It's soft. It's designed to be thrown. So that way we can efficiently get the microphone to the person who needs it. Who wants to be the first person to ask a question in the stand microphone? Close enough. Let's get that thing going. See, soft. Very good. Nice catch there. Anybody have an actual question? Jaylene?
No.
Yes. Yes, it is. All right. So park that thing over there. I'm sure somebody will have a question as we go along. Talking more about probability with discrete random variables. We'll get into the case of continuous random variables next week. Next week, we will also have to do this obligatory disclosure that I work at Columbia. You go to school at Columbia. Columbia gets money to develop STAN. Use STAN. Try to make money according to Columbia University policy. That creates the appearance of a conflict of interest. Should be aware of, even though we're not talking about STAN today. I did not want to try Safari. Okay. No. Damn. Didn't I click no? All right. There. Did I lose my... Right. Zoom back in 3 times. Make sure. All right, we're going to take a brief pause in the... No, we're not going to pause. Hopefully it's still working. Okay, so go into full screen mode. I did that. Okay, if you source this URL, you can get the file. It's on Coursework, Canvas, the same one we had last week. Pretty much, it will load in the function to calculate the Fibonacci numbers, the function to calculate the probability, which is the ratio of the xth Fibonacci number divided by -1, plus the nth plus 2 Fibonacci number. Then we constructed the sample space omega, which is going to be all the integers between 0 and 10. And then we did a loop to construct this table that you see here, the joint probability of two things happening on two rolls in the same frame of bowling. Again, the row pertains to the number of pins ostensibly to be knocked down on the first roll of the frame of bowling. The column pertains to the number of pins being knocked down on the second frame of bowling, and the probability in the interior cell is the probability that both the thing in the row happens and the thing in the column happens. Those numbers, probability, formed by the general multiplication rule, and hence are going to add up to 1, but they add up to 1 given that 55 of these things are 0, because it's impossible to knock down more than 10 pins in the same frame of bowling. So any questions about that from Thursday? And for those of you with the laptops, if you source in this URL, it will run all the code to generate this table of bivariate probabilities here. Everybody got it? Or the files on Courseworks. It's just the same one as last week. So it's in week 1 on Canvas. All right. So no questions about that? All right. Okay. So if here we have put the entire sample space omega into our probability function, we get back numbers. They're between 0 and 1. They add up to 1 for the marginal probability of each thing happening on the first roll of a frame of bowling. And based on this information, what is the mode of the distribution for the number of pins on the first roll of a frame of bowling? 10. And how will we define the mode?
Most commonly occurring number.
All right, the element of the sample space with the highest probability, assuming it to be unique, which it is in this case, and so it's 10, or a strike is the mode. So 10 is the mode, 0.384 is the modal probability, and 0.384 is greater than any other probability under the assumptions that we've made here about our data generating process. Okay. If that is the mode, what is the median? 9. And how did you arrive at that? Appears at 50%. That's basically right. We need to be a bit more precise in the case of discrete random variables about what to do with sort of when none of the elements exactly have cumulative probability of 0.5. So the median is the smallest element of the sample space such that at least half of the cumulative probability is less than or equal to that element, and consequently at most half of the probability is greater than that element. So we can see in this case 0.237 and 0.384 is sort of minimally greater than 0.5. So that means there is more than 0.5 probability that is less than or equal to 9. 9 is the smallest such number where that is true. So 9 is the median number of pins knocked down, even though the cumulative probability that it's less than or equal to 9 is a little bit above 0.5. In fact, it's, you know, yeah, it's a bit above 0.5. Everybody, it's easier in the case of continuous because something's going to have a cumulative probability of exactly 0.5, but in the discrete case, we have to adjust or clarify the definition of what a median is, because usually things are not going to come out exactly 0.5 for cumulative probability of any of those elements. Questions about medians? Okay. So what is the expectation for the number of pins to be knocked down on the first roll of a frame of bowling? 10? Right. So expectation is kind of a weird word in English, and we're using the statistics or probability version definition of expectation, which is a bit different from what expectation means in English. So when you say like you're expected to show up on work on time or something like that, one, it's sort of normative rather than merely a descriptive statement. But two, you're sort of anticipating that the expectation is going to actually happen. Maybe not guaranteed, but that's like, you know, the most likely thing. And so when you say expectation to someone just in English, I think they probably think about the mode if you sort of define it specifically. But the expectation of a discrete random variable has a very particular definition that you're just going to have to memorize because it's a very important concept in probability that was alluded to in front here. The expectation of a random variable is defined as the sum over the entire sample space of the product between each element of the sample space and its corresponding probability. So the expectation is also going to be a single number. It can be either positive or negative if the sample space contains positive and negative numbers. But in this case, the sample space only contains non-negative numbers, so the expectation is going to be positive. The expectation is such a fundamental concept in probability that it has its own Greek letter, the lowercase mu over here. So when you see a mu, that usually means that this is going to pertain or is actually the expectation of some distribution. So we see that the expectation is just a probability weighted sum. Question, Sheng?
For the median?
I got it. Talk to me. Yeah.
For the median, you say like the first half of the probability, are they like the smallest half?
Yes. So when we're calculating the median, we want to accumulate the probability that's less than or equal some element. When that crosses 0.5 for the first time, then that is the median of a discrete random variable. And in this case, it's 9.
I mean, you have to rank the probability.
No, it's in order of the sample space. So you know, if the probabilities were different, the median could have been 6. But in this case, it's 9 because we have to add up all the probabilities until we get to 9 in order to cross 0.5.
What if like the 0 got a 0.4?
So if 0 was 0.4, then 0 would not be the median, but 1 might be. So if it went 0.4 and then 1.15, then 1 would be the median. It's the first value of the sample space where the cumulative probability crosses 0.5.
So are you saying that the sample space has a small number in it?
Yes, or in this case, it does. So the median only applies to sample spaces that can be ordered, like number of pins knocked down, small, medium, large. But if we say we had a sample space for what state do you live in, that does not have a unique order. And so the median state of residence isn't really a well-defined concept. However, if we say median income or median education, that would be. All right. So expectation is a probability weighted sum. And that's a very important concept. If you work out the math, it's 8.431 here. Now, nobody in the history of bowling has knocked over 8.431 pins on their first roll of a frame of bowling. So even though the sample space consists of 11 integers, the expectation of that random variable is a real number, because probability is a real number times integer is real number, sum of real numbers in general is going to be a real number. And so the expectation of a discrete random variable is generally going to fall outside the sample space. Although in this case, well, in every case really, if you have the expectation of a discrete random variable, it will be between the minimum and the maximum of that sample space. But it's not going to be an integer. In general, it'll be a real number. The mode and the median of a discrete random variable are going to be discrete if, the sample space is discrete. Does everybody understand difference between mode, median, and expectation? All three are sort of summary measures of a location of a random variable, but they're different measures. And of the three, the most important is expectation. And then the next most important is median. And the not very important at all is the mode. Good so far? Okay. So when you talk about expectation or the mean or something, people automatically think of the average. I just take a bunch of data points, add them all up, divide by the number of data points that I have, and that's like the average. And what I want to show on this is that the average that you all and pretty much everybody else are familiar with is an estimator of the concept known as the expectation. And to see that, let's sort of define the expectation of y as the sum of y times the probability of y. Now let's say we're going to estimate the probability that y takes on a particular value with 1 over n divided by, or 1 over n times the sum of these indicator variables where y sub n, the nth data point, is equal to the value of y in question. So we're going to estimate the probability that y is 0 or 1 or whatever y wants to be with the proportion of observations in our data set where that number for y comes up. So if we estimate a probability with a proportion in the data, then let's just take this definition of the expectation here, substitute in this proportion where we have a probability in the definition that has a 1 over n, which we can bring to the left of the double summation. And so we have 1 over n times the sum over the sample space of y times the sum of these indicator variables over the observations. And if you simplify that down, you move y interior to the double summation, then what you're left with in the end after doing some simplification is 1 over n times the sum of the n observations that you have in your data set, which is just the familiar expression for the average or the sample mean. And so you can see the sample mean as being an estimator of the concept of an expectation with a very particular, albeit perhaps reasonable, estimator of the probability as the proportion of y equal 2 or whatever that you have in your data set. So there's lots of people who can calculate an average in R. You just do like mean of a vector and comes out some number, but not that many people can say what the average is estimating. Can't define what you're estimating when you calculate the sample average. And, this may be a good estimator if you have a sample that's one large and a simple random sample from some population. Then the proportion of observations that are equal to this or that converges pretty rapidly to the true probability. So it's a decent estimator. Under other conditions, it might not be such a great estimator. But at best, it's an estimator of the concept, and we want to be very clear as to what the concept is. So if you do simple random sampling from some population, S times, as S goes to infinity, this sample average is going to converge to the true expectation. The true expectation being a property of the random variable rather than a property of particular realizations of the random variable. But with realizations, we can estimate it. And so here we see at the bottom, I've calculated the exact expectation of a first roll of a frame of bowling by taking omega, multiplying it element-wise by the probability of that occurring, and summing it all up. And that is approximately the same, or that's the exact number. And we can approximate that with a mean of a huge random sample using the sample function from the set omega using the probabilities that we have here to draw. So if we do that like 10 to the 8th times, it's going to be a very good approximation of the exact value, but it's only an approximation. The concept that we're interested in here, at least this week, is with the expectation, and we want to keep concepts and estimators of concepts mentally distinct. Questions about that? Okay. So let's practice a bit. How would you calculate the expectation of the second roll of a frame of bowling given that 7 pins were knocked down on the first roll? Let's not try to get an exact number, but conceptually, how would you do that?
You would calculate the conditional probability distribution.
What specifically? Which one?
Basically, all the different cases conditional on knocking on 7 in the first round.
Right. So that would give you conditional probabilities. And what would you do with them?
The weighted sum.
Right. Use those probabilities in a weighted sum of the subset of the sample space that's possible when 7 pins are knocked down. So 0, 1, 2, or 3. And so in this case, you could do it with the trailing ones, but those are going to have 0 probability. And in this case, that conditional expectation comes out to be 2, because you take 1/7 times 0 plus 1/7 times 1. So we have 1/7 plus 2/7 times 2. So added those together, that's 5/7 plus 3/7 times 3. So that's 9 and 5. So 14/7, which is 2. So if you put conditional probabilities into the formula for an expectation, you get a conditional expectation. If you put unconditional or marginal probabilities into the formula, you get an unconditional or marginal expectation. So different ones of those can be useful in different circumstances, but it's pretty much the same formula. You're just changing what probabilities you use. All right? More practice. How will we calculate the expectation of the second roll of a frame of bowling, irrespective of what happens on the first roll of that frame? Uh-huh.
Because we don't, it's irrespective of one, we need the marginal probability of doing the second roll
Right. So we would take our joint probability table right here. And then how will we get the marginal probabilities for the second roll? Yes, which sum? Right, the sum down the columns gives us the probability of knocking down that number of pins on the second roll, irrespective of the first, because let's take the example of 9. So if 9 pins are being thought of as knocked down in the second roll, it could be either 0 and 9 or 1 and 9, but nothing else, because that's impossible. So we add up those two. That gives us the marginal probability of knocking down 9 pins on the second roll. We could do that for all the columns, and now we have a vector of probabilities for marginal probabilities for the second roll. We use those probabilities, multiply them element-wise by the sample space, add it all up, and now we have our marginal expectation for the second roll of a frame of bowling. So in mathematical symbols, we want to get the probability that x2 is equal to something, multiply it by those, add it all up. In order to do that, we need to sum over the joint probability for all possible values of the first roll, which is indicated by xi here. And we can express the joint probability of what happens in 2 rolls in the same frame of bowling as a marginal probability for what happens on the first roll times a conditional probability for what happens on the second. This piece here gives us the marginal probability for the second roll, or equivalently this one. And then we multiply that by all the things that can happen on the second roll, add it all up, and that's our marginal expectation for the number of pins knocked down on the second roll. So just to do that in our code, we first take the column sums down our table of joint probabilities. That gives us a vector of probabilities that will sum to 1. In order to get the expectation of the second roll, we take the sample space for the second roll, multiply it by the marginal probabilities, add it all up, and we get expectation for the second roll, 1.064 something. So the expectation for the second roll is a very different number and a very different concept than the expectation for the first roll, which was 8.43 something. Because we used a different set of probabilities, even though we were weighting the same sample space in this case by those probabilities. Everybody got that? Okay. So the good thing about expectations, they really only involve multiplication and addition. So you would expect rules like the distributive property or associative property to work when dealing with expectations, and they do. So an example of that, what if we think of the expectation of some constant c times a random variable x? What is the expectation of that product if c is some constant?
Is c times the expectation of the variable.
Right, and how did you arrive at that?
Because c is constant, so if you can take it out from the...
Something like that. So we have c times x times the probability of x, but c is a constant, so we can bring it out front of the sum. And we have x times the probability of x summed over the whole sample space, which is just mu. So we have c times mu. And that makes sense. So the expectation of a constant is a constant. The expectation of a constant times a random variable is the constant times the expectation of that random variable. Good? Okay. So what is the expectation of the sum of 2 rolls in the same frame of bowling? how would we go about calculating something like that? Right?
You go back to your table. Each cell represents a total as well, right? So if you sum the column header and the row header for each cell, you have the expected or the value for that cell. So you overlay that on top and do some product on top of all that, you get the expected value.
All right. So one thing we could do is take all these probabilities, multiply them by a table that is of the same size that has the sum. So if you were like 2 and 7, like in this cell for the other one would be 9. And we just overlaid those two on top of each other, element-wise, multiplied them together, added it all up. Yes, we would get the expectation for the sum of 2 rolls of a frame of bowling. But there's another way that we can go about calculating that. So we have, purple is not a good color for me. Yellow is not that good a color for me. Do we have any? All right. So that is going to be a double summation. But we can simplify this down. So first, we can call this just expectation x plus all right. So all I've done here is take my sum of 2 things and break it into 2 sums just by distributing the x plus y across the probability. So now I have 2 sums. But one of the things I can do is, since this is a sum of x over y, I can take x out of the interior sum and put it over there in the middle. Because first we have a sum over x, then we have a sum over y. So I can take the part that only depends on x and put it in the middle here. So this second part the sum over all possible values of y of the joint probability between x and y. What's that? Patrick? Probability of x. So this whole thing here is just the probability of x. And if we do it over here, I'm going to switch the order of the summation, which is legal because it's addition. And then I'm going to move my y interior. So what's this? The sum over all elements of x of the joint probability between x and y. Probability of what? So up here we have x times the probability of x summed over all elements of x. What's that? Expected value of x. And down here I have the sum over all elements of y, of all elements for the sample space for y, of y times the probability of y. What's that? So all together, what have we shown? That is what we have shown. Expectation of a sum is the sum of the expectations. That holds not just for 2 random variables, but for any number. And it holds irrespective of whether X and Y are independent. And indeed, in the bowling case, they are not. Moreover, it holds if we have some constants in there, multiplying them, you know, then you have to carry the constants around. But it's the same deal as what we said before, where you just pull it out front of the sum and then you multiply. So expectation is a linear operator. Sum is a linear operation. And so we get, you know, results in this case, like expectation of a sum is equal to the sum of the two expectations. That's particular for the expectation. Some other things that we'll see that are kind of like this, there'll be one general form and then some simplification if the random variables are independent. But actually, this one is true irrespective of whether X and Y are independent of each other. Does everybody see how we did that? It's just distributing, factoring, switching the order of addition, recognizing, you know, what something simplifies to, and then, you know, carrying it through. Questions? All right. So here I actually calculated up that table that was being referred to. So if you just call the row function and the call function, that returns the row index or the column index respectively of a table, and we subtract 1 to make it start at 0. So we get this matrix here, S. So all of the numbers that are in red can't actually occur, but in general, the cell is going to be the sum of the row index and the column index. So 2 and 5 is 7, etc. So we have that matrix S, and we can get, like we said before, just kind of by brute force, sum of the joint probabilities, element-wise multiplied by S, add it all up, and we get an expectation for two rolls in the same frame of bowling of about 9.5. But that 9.5 is suspiciously identical to 1.064 something plus 8.431 something, because expectation of a sum is the sum of the expectations. Good? So remember, the random variable is a function. So essentially what we've done so far is take the expectation of a function. But the formula that we've learned for taking expectation actually applies to any function of a discrete random variable. So if g of x is some function, any function, inclusive of the identity function, but any function, then its expectation is going to be given by the expression, the sum over the whole sample space of the random variable x of the function value times the probability that the x input is, you know, that value, summed up over the whole sample space of the random variable x. That gives us the expectation of g of x, where g of x is any function that we want. However, one classic thing that trips people up is the expectation of a function is not equal to the function evaluated at the expectation, at least in general. Now, for linear functions, that happens to be true. But for nonlinear functions, it's not true. Consequently, it's not true in general that the expectation of a function is equal to the function evaluated at an expectation. And so you want to do it the right way rather than trying to take a shortcut when the shortcut is wrong. But the formula for the expectation of a function of a random variable, discrete random variable, is no real much harder than what we did before. It's just evaluate the function, weight it by the probability, sum it up over the entire sample space of the input, where the input is a random variable. Get an expectation of a function of a random variable. And since a random variable itself is a function, any function of a random variable is itself a random variable. So now we're taking the expectation of the random variable g of x, but we don't need to know anything about the distribution of g of x in order to calculate its expectation. As long as we know that the probability of x is this and this and this and this, we can weight, sum, and get the expectation of g of x. And some expectations, the expectations of some functions are so fundamental for probability that they have special names. So if we take a particular function, g of x, namely x minus its expectation quantity squared, the expectation of that function is known as the variance of x. So the expectation of the function x minus mu quantity squared is the variance, and it has its own Greek letter, lowercase sigma squared. Can also be shown that sigma squared, the variance, is equal to the expectation of the square of x minus the square of the expectation of x. And that can be shown by expanding out x minus mu squared into terms. So why don't you see if you can show, using the linearity of the expectation operator, that it's true that the variance is equal to the expectation of the square minus the square of the expectation. Meanwhile, I will erase this previous row. All right. So we start, everybody agrees that x minus mu quantity squared can be expanded out. X squared minus 2x mu plus mu squared. So if we write it like this, what would be our next step in order to show that this is actually equal to the expectation of the square minus the square of the expectation? Right, so distribute this over here. So let's just take this first part here. So the probability of x times the function x squared summed over the whole sample space of x. What's that? Expectation of the square. Okay, so that part's dealt with. And then we're going to have probability of x times negative 2 mu x. So that's going to be minus 2 mu. We can pull out the 2 and the mu because those are both constants. Sum over the sample space of x. Probability of x times x. So what's that? Expectation of x. So really I have 2 mu squared. And then finally I have the sum over x of the probability of x times, that's a mu, obviously, times mu squared. So what's all that? Mu squared, because mu squared is a constant. I could even bring it out here. And the sum over x of the probability of x is just 1. So mu squared times 1. So that leaves me the expectation of x squared minus 2 mu squared plus mu squared. So it ends up being expectation of the square minus the square of the expectation. Everybody see how we did that? Distribute, group things, simplify, factor, recognize the patterns. All right? So sigma being the positive square root of sigma squared, the variance. Again, or maybe this is the first time I've said so, when I take the square root, I always mean the positive square root. So the square root of the variance is called the standard deviation. Standard deviation is not an expectation of anything, but it's a function of an expectation, namely the variance, and the variance is the expectation of x minus mu quantity squared. Standard deviation more common as a measure of dispersion of a random variable because sigma will be in the same units as x, whereas the variance sigma squared will be in squared units, which is usually not as intuitive to deal with. If we let g of x be negative log of the probability of x, the expectation of that function is known as the entropy. And the entropy is an interesting function because it reaches its upper bound when the probability of x is a constant, which is to say it's the same for every element of the sample space. So the entropy is a measure of how uniform a discrete random variable is. Higher entropy, more uniform; lower entropy, less uniform, more concentration. And it's going to be a non-negative number. In this case, it's 2.36, but that's not as relevant as the concept of taking the expectation of some function. And some functions are special, so they have special expectations with special names, but it's the same formula. Take the function, weight it by the probability, sum it up over the whole sample space, and you're done. Questions? So one function that you might want to take the expectation of is utility. And this can be embedded in a relatively straightforward and easy to understand procedure for making decisions. So it oftentimes seems sensible to make a decision that maximizes expected utility, where utility is some function, and we know how to take the expectation of a function. So in order to make the decision that maximizes expected utility, you first need to enumerate the possible decisions that could be made that are under consideration. Those decisions are not random variables. They're just decisions. Then you need to define a utility function of the decision and other stuff like random variables. It can also depend on other known qualities. Now, if we're going to take the expectation of something, we're going to need some probabilities to weight with. And the best probabilities to use are the probability of what you don't know given what you do know, which is to say posterior probabilities given by evaluating the right-hand side of Bayes' rule. So you update your prior probabilities into your post probabilities by conditioning on the data that you know to get posterior probabilities, and use those posterior probabilities of what you don't know given what you do know as weights in the weighted sum that defines the expectation of utility. And then you calculate all those expected utilities for each of the decisions under consideration, make the decision that maximizes your expected utility, and you're done. So that seems pretty reasonable. The only complicated, well, you do have to, one, enumerate the decisions under consideration, and someone, ideally whoever is making the decision, needs to specify a utility function for the decision. But in, let's say, a business context, you can always get away with taking profit as your utility function. So what decision that a business could make maximizes expected profit? The difficult part of that is going to be getting the probabilities to weight profit in order to get expected profit. For that, you have to use Bayes' rule. To get those, you're going to have to use Stan. To understand how to use Stan, you're going to have to take a class. But the rest of it is all pretty straightforward, intuitive, sensible, and comes up with a sort of well-justified way for making decisions that maximize expected profit or whatever your utility function might be. Sounds easy, right? Sounds simple, intuitive. It is, except for the part where you get posterior probabilities. But the framework of it makes sense to most people, not the people in the School of Professional Studies who fired me for proposing that I teach this in their course. But that's okay. They also fired the guy who fired me. But you're going to have a hard time just rolling into a business, for those of you who work in the real world, and be like, okay, this is how we're making decisions now. Because although most businesses or whatever, if you say, okay, you know, we're going to make decisions that maximize expected profit, they're like, yeah, okay, we should do that. Definitely. They don't really know how. And they're not that committed to taking the steps that enable them to do that. So the typical procedure for making decisions in, you know, one of those companies is that whoever is making the decision, like, sends an email to some person that they just hired, like last week or whatever, and says, can you write up a one-page memo, you know, analyzing the data and what for like different options or whatever, and then like send it back to me by the close of business on Friday. And then, you know, whoever does that writes up the memo, sends it off, and the person who requested the memo takes it, reads it maybe, and then makes the decision somehow, but not following any sort of rigorous procedure like this. There's no probabilities or utility function or, taking expectation or anything like that, even though that is probably well within somebody's capability. And that's because in a lot of these organizations, they're not really asking someone who they just hired last week in order to make some important decision from them. Really, whoever wants to make the decision already has a decision that they prefer in mind and are looking for a rationalization of that decision, rather than saying, okay, we're going to apply decision theory and then, whatever the expectation gets maximized, that's what we're going to go with. Really, they already have a decision in mind and are looking for someone to validate what they've already decided. And that can yield disastrous decisions. But, with the professional incentives and things like that, no one wants to give control over the decision-making process to an algorithm or a procedure like this if they're going to be held responsible for those decisions. Because you can only make the decision that maximizes expected profit. Realized profit after you've made the decision can be, anything from the conditional probability distribution of that decision. Things may go your way, or they may not. But at the time you had to make the decision, making the one that maximizes expected utility makes sense, even though you're not going to find that many businesses who try to do this explicitly. Maybe a little bit of insurance and investing and things like that, where this idea of expectations already comes naturally. But in your sort of typical, we have a website and we sell stuff, you're not going to see this being practiced, even though it probably should. Assuming you have somebody in your company who can get the posterior probabilities for you, then it's easy. Questions? Iterated expectations. Expectation of a conditional expectation is a marginal expectation or an unconditional expectation. And so if we have interior, the expectation of y, given that x takes a value little x, that's just y times the conditional probability of y given x. And we want to take the expectation of that function in brackets here with respect to x. So that's going to be the sum, probability that x is equal to little x, times the conditional expectation of y given x on the previous line. So we have probability of x here, conditional probability of y given x over here. Multiply that so everything's interior. We have conditional probability times marginal probability, which is what? Joint probability here. So if we have the sum over x and y of y times the joint probability, we can switch the order of the summations in order to factor out y, put it interior. So now we have the sum over y of y times the sum of the joint probability summed over x. What's the joint probability summed over all the possible values of x? Probability of y. Y times the probability of y is the expectation of y mu y. So if we weight conditional expectation of y given x by the probability that x transpires, sum it up over all values, possible values of x, we get the marginal expectation of y. Again, this pretty much just relies on the fact the expectation is a linear operator, just doing summation and multiplication and factoring and distributing and switching the order of stuff, etc. Got it? Covariance and correlation. So what we talked about before, the expectation of some function, also applies to a function that has two random variables of its inputs. So we define the function g of x and y, where x and y are both discrete random variables, and we take the specialization, g of x and y is equal to x minus its expectation times the quantity y minus its expectation. The expectation of that g function, which is the sum over the sample space of both x and y of that function multiplied by the joint probability of x and y. That function expectation has a special name, and that name is covariance. If x and y happen to be the same random variable, then the covariance of x and y simplifies down to just the variance of that random variable, because x minus its expectation and y minus its expectation would be the same thing. But in general, x and y can be different random variables. Indeed, random variables defined on different sample spaces. And the covariance between them is the sum over both sample spaces of this function here, weighted by the joint probability of x and y. The expectation that you get by doing that double summation is the covariance between x and y. If we define a function g of x and y, where x and y are random variables, as like the same thing, except we divide each by the respective standard deviations. So we have x minus y divided by the standard deviation of x, and y minus the expectation of y divided by the standard deviation of y. The expectation of that function is known as the correlation, and it can be obtained by pulling the expectation of x and the expectation of y outside the sum, which is legal because those are constants. Then inside the double summation, we just have the covariance that we had before, leading us to the conclusion the covariance is equal, correlation is equal to covariance divided by the standard deviation of x divided by the standard deviation of y. And correlation is probably something that you're already familiar with, or at least the estimator of a correlation, or put a bunch of points on a plot and draw a line through them and say, you know, this is positively correlated or whatever. But correlation is a well-defined concept. It's the expectation of a particular function, and we can estimate that correlation if we want. But in doing so, we have to keep separate in our heads the concept from the estimator of a concept. And the concept is fundamental enough that it has its own Greek letter, rho, and it usually is associated with the correlation. Both the covariance and the correlation are measures of linear dependence between x and y. The covariance will be in the combined units of x and y, whereas the correlation, because it divides by standard deviation and standard deviation of x and standard deviation of y, cancels the units, and it's a unit-free measure of linear dependence that is combined to the -1 to 1 interval, whereas there's no such constraint on a covariance because it's in the original units. So that brings us to the question, is the correlation between two rolls in the same frame of bowling positively correlated, negatively correlated, or about zero? And why? And how? Did you come up with that?
I was thinking it might be close to 0.
And why did you think that?
Because if you like knock down more of the pins,
Pins?
in the first round there are more left to hit the next one. But if you didn't hit many in the first round, you might not be a very good bowler in the first place. So I think those two might sort of
So how good of a bowler you are is sort of defined by the probabilities that we specify. So you could get unlucky and sometimes get a 2, even though that's not so probable. But around 0, maybe. Anybody else? Patrick?
Negative.
Negative.
So like if the formula is sigma x and sigma y are positive, so it just depends on like the
Yeah.
x minus u x, y minus u y.
Mm-hmm.
And so if x is your first row and you roll something higher than average, then y is probably lower than average. So that product is negative.
So they would tend to have opposite signs, and if you sum up things that are negative, then you tend to get a negative number. Yeah. So one way to think about it is there's an exact linear relationship between x1, the number of pins you knock down on the first roll, and the number of pins available to be knocked down on the second roll, which is 10 minus x1. So there's an exact negative relationship between x1 and 10 minus x1, the number of pins available. And since there's a strong and positive but not perfect relationship between the number of pins available to be knocked down on the second roll and the number of pins actually knocked down on the second roll by a decent bowler, then it would stand to reason that there would be a negative, albeit not perfect, relationship between the number of pins actually knocked down on the first roll and actually knocked down on the second. But we don't need to speculate about it. We can calculate this in R pretty easily. So we get the expectation of the first roll, and then we just initialize covariance to 0, loop over the sample space of the first random variable, loop over the sample space of the second random variable, at least the ones that have positive probability, increment covariance by the difference between x1 and its expectation, multiplied by the difference between x2 and its expectation, always weighting by the joint probability that that happens. So when we come out of the loop, we have some number there. Then we can get the variance of x1 is just taking the sum of this function here, weighting it by the marginal probability of x1. We can get the variance of x2 by weighting by the marginal probability of x2, this time subtracting x2, expectation of x2 rather than the expectation of x1. And then if we divide the covariance by the square root of the product of the variances, that's the same thing as dividing by the product of the standard deviations. And that gives us the correlation, which is negative 0.88 in this case. It's just applying the definitions and doing some arithmetic, and in this case, doing some coding to calculate that in R. Question? So the variance of a sum can be calculated in a straightforward fashion. Just subtract the expectation of 2 rolls from each element of S, square that up, weight it by the joint probability of everything. So that's going to put 0 probability on all the things that can't happen. You get the variance of the sum of 2 rolls in the same frame of bowling, which is about 0.8 in this case. But 0.8015148 also happens to be exactly equal to the variance of x1 plus the variance of x2 plus double the covariance. And that, in fact, is true in general, not just for bowling, not just for this probability function, but in general, the variance of a sum is equal to the sum of the variances plus twice the covariance between those two random variables. And how might you go about showing that to be true in general? Maybe something to try on your own, but I would expand the square when you do that, and then see what the implications of that are. Last thing for today, want to start talking about the Bernoulli distribution. And so the bowling example we've done so far is very neat, and that it illustrates all the concepts we need for discrete probability. But it's not all that useful because we just assumed here the probabilities, and that gives us a distribution for pins falling down. A much more common thing would be to say, how can we estimate the probabilities given the data that we have on pins falling down for some person as they bowl? And for that, we're going to need probability distributions that have parameters in them, which the probability distribution we've been using so far does not, and that limits its usefulness. So we could get the probability that x is equal to 1 if there's one pin standing on the second roll just by plugging in this. It gets 1/2, but that's not the most general way of assigning a probability distribution when we have a sample space that's just 0 and 1, failure and success, no and yes, whatever 0 and 1 correspond to. The more general way of giving a probability distribution for that kind of sample space is known as the Bernoulli probability distribution. It involves a known or perhaps unknown parameter pi, which is going to be a real number between 0 and 1 inclusive, known as the success probability. And so the probability of failure that x is equal to 0 is just going to be 1 minus pi. And we can write both of those cases in the same expression. Probability of x given pi is equal to pi raised to the power of x times 1 minus pi raised to the power 1 minus x, where the sample space here is 0 and 1. So if x is 0, then we have something raised to the power of 0, which is just 1 times the probability of failure raised to the power of 1. And the other way around, if x is 1, then we have pi to the 1, which is pi times something raised to the power of 0, which is going to be 1. So pi times 1 over pi. So this is really the only distribution you can be using when your sample space is failure and success. So what is the expectation of a Bernoulli random variable? Probability of success. And did you obtain that by taking 0 times the probability of failure plus 1 times the probability of success, and you got the probability of success? Good. And what expression is the variance of a Bernoulli random variable? What is it? X minus its expectation quantity squared times the probability that x is 0, which is 1 minus pi, plus 1, so x is 1, minus its expectation quantity squared times pi. We simplify that down, we get pi squared 1 minus pi plus 1 minus pi squared times pi. Factor out the 1 minus pi. It left with pi plus 1 minus pi times pi. Anyway, this comes out to pi That's 1 minus pi squared. If you simplify it down, which is nice, but the main thing is just to know in general that we get the expectation of a random variable by taking the function x minus its expectation quantity squared over all possible values of x, weighting by the probability that that occurs. All right. So we will pick it up on Thursday. Talk more about these probability distributions for discrete random variables that have unknown parameters in them, such as pi. But we're going to want to continue to do these operations that we've been doing, multiply marginal by conditional to get joint, marginalize over joint, divide joint by marginal to get conditional, as in Bayes' rule, take the expectations of marginal and conditional and joint probability distributions, take the variances, take the entropy, take the utility, expectation of anything we want. All we have to do is apply what we know. So we'll see you then.